then in comparing those two, you not only get the direction of travel, but you get a velocity from that. And that's how radar sensors or Doppler sensors work. And that was found by somebody playing music, and I think I told you the story, and you could hear, or actually a train whistle blowing, and you could hear it at a different frequency coming at you than going away. Same concept. It sounds different because it's a different frequency of the sound. Okay. Matter of fact, I think it's a higher frequency coming at you because, and thus it's a higher sound, and then lower frequency going away, so it sounds more bass. Lower. So, that's the concept of the Doppler principle. Now, that's very important when we get into calculations. And at some point, I'm going to need to probably find an overhead, something to write on the board, but we'll get to that in a bit. First thing that I want to talk about is not your assignment, but talk about combines. How many people have seen a combine working? Good. How many people have actually been in the combine? It's kind of neat, isn't it? A lot of neat stuff going on in that combine. But it's important, I feel, for yield mapping to know how a combine works. So, I am going to bring that down. And we're going to talk about combine performance. Thinking I can zoom. Because if we're talking about yield, we're trying to measure the yield at the combine itself. Okay, so how does a combine function? There are several components of the combine. When the material comes into the header, as what's called here, it gathers that material, well, it cuts it, and then it gathers it. It brings it together. Okay. Then, that material is transported up this chain drive, and usually being threshed at that point. And that's what they refer to as the concave a lot of time. There's some screens there in material. So you're sort of breaking the material apart. You're taking the husks off the corn. Here you're taking the cobs off, the ears off the stalk. And here you're taking the husk off of it. And then it goes through that concave and starts to separate it. So you have a threshing and a separation in which, if the corn's dry enough, and you hope it's dry, you're pulling the kernels off the cob as opposed to mashing the kernels. If it's too wet, you end up trying to separate it and just mash it. It has to be down to 12% or some moisture content, 10% in order for that good separation. And then you take that material and you need to clean it. And that cleans the chaff or the small stuff out of it. So a lot of this is a sieving process as it moves through, and this is coming directly out of the book, and there's some arrows that are hard to read, but there's a lot of sieving that goes on, and then the kernels fall through, but also a lot of litter falls through too. And so at some point then you use air to remove the chaff and the litter from the kernels themselves, which tend to be more dense and less aerodynamic. You can throw air through it and it just throws it back. Matter of fact, in the old days, they used to throw grain up in the air and blow on it. Or they have a fan that blow all the chaff out and keep the grain kernels. And then at that point, it drops down here, and they feed that back up into what's called the clean grain column. And that's where they keep that during the process. So you cut, you gather, you remove the ears if it's corn, you thresh, you separate, you then clean, and then you store that into the clean grain hopper. And that's kind of the process of capturing and combining. Where's the yield measured during this whole process? Is it what? By weight? Well, that's a good point, because you could actually weigh that clean grain auger. And a lot of people do that, or they try to do that, as you're moving, and the more stuff in there, the heavier that clean grain auger. And sometimes on those conveyors, you can actually weigh those conveyors and see how heavy. There's more material in there, there's more material in those conveyors. So that's one way to do it. But weighing the clean grain tank, bin, is one idea and works well if you're static. But if you're driving through the field, there's a lot of vibration and acceleration. So if you're looking at the weight, it's just kind of flying all over the place. Yeah, it's increasing, but you're seeing a lot of acceleration. So that's one way that's not been very useful. How else would you, on the go, measure clean grain?
Flow.
At the where?
Flow.
At the flow. You're measuring the flow of the clean grain. Well, where would you do that?
I don't know.
Okay, typically that's done at the clean grain auger as it's going into the tank. And when they call that an impact sensor, you have a sensor up there, and what's coming out of the clean grain auger is actually material that's flowing, and so you're measuring flow, and it hits this impact sensor and drops down. So, what happens though is, in the old days, the old clean grain auger would have a little flapper valve. And so as this material is hitting it, the more material that's coming through, the higher the mass flow rate, the more this little flapper valve would actually move. And then you used a potentiometer on that flapper valve to measure the angle of that valve, that little plate. And then the higher it's moved, the more it's moved, the higher the mass flow rate. And when we talk about flow, we're referring to a mass flow rate, not a volumetric flow rate when we talked about sprayers. That's liquid. Here we're talking about mass flow rates. Now, they don't do that anymore. So that answer to that one question is, how do you measure on-the-go yield? And what device is used for that? And the answer in the text, that's called a potentiometer, is used to measure the displacement of this impact plate. That's kind of the old days. The new day is that impact plate, it is now fixed. It doesn't move back, it's fixed. And as the grain hits that, it measures essentially the force on that impact plate. That's why it's called an impact tester. Now that force on that impact plate has two components to it. One is how much of that material is actually coming in. If I just threw one little kernel at it and hit it, the force would be relatively low. But if I'm throwing a bunch of kernels at it, the force is going to be higher. So it has to do with the mass, but it also has to do with the velocity at which that material is hitting it. So you have this concept of mass and velocity to indicate some sort of force. And typically, that impact plate, the force of that impact plate is measured with a what?
Strain gauge.
A strain gauge, just like a regular force transducer would be. And this thing doesn't flap around or change its angle. It just sits there and maybe moves a little bit. It's got to strain a little bit if you apply a force on it. And so there's a strain gauge that measures that force. And so that's the typical way of determining the force on the strain gauge. There are numerous, and that's what's being shown right here. As we take a look at a clean grain elevator or auger that's throwing material over here, we have some sort of mass flow sensor. There's an impact plate here, and it's dropping down into here, and it's measuring that force. What are some of the other ways? We talked about weight. We talked about impact, and this is, I would say, probably 95% of the devices I've seen to measure grain flow use this type of either an impact plate